In this film, we shall discuss the extremely important idea of function from the point of view of sets. Teachers need no arguments to convince them that function is one of the central concepts of mathematics, but they may not be familiar with the modern formulation of this concept. We begin by supposing we have a set of numbers, any set of numbers at all, which we shall call U, and indicate how to form a special set of ordered pairs from it. For the sake of simplicity, we shall use an easy special set for U. Suppose our set U consists only of the three numbers 1, 2, and 3. Then all possible ordered pairs can be obtained in this way. With 1 as the first coordinate, we get 3 ordered pairs. Using the number 2 as first coordinate gives us 3 more. And from number 3, we get the final 3 pairs. Of course, the pair 1, 2 is not the same as the pair 2, 1. The set of ordered pairs obtained from U in this manner is denoted by this symbol, read U cross U. We can exhibit U cross U graphically by interpreting its pairs in terms of the usual rectangular coordinate system. X always refers to the first number of the ordered pair xy, and y to the second. X is the distance across, right or left. Y, the distance up or down. A second example will help to clarify the idea. This time, let U be all the positive integers, not just the numbers 1, 2, and 3. For this U, the graph of U cross U will include all points in the first quadrant with integral coordinates, the so-called lattice points. U cross U depends entirely on the replacement set, or U. If U is the set of real numbers, U cross U includes every possible ordered pair that can be made up from 0, the positive and negative integers, fractions, and irrational numbers. The graph of this U cross U includes every point in the plane, without exception. Sets of ordered pairs can be associated with sentences in 2 variables, such as these. Such sentences are neither true nor false by themselves. They only become true or false for certain replacements for x and y. For example, if x equals 1 and y equals 5, the sentence y equals x plus 4 is true. But if we reverse the numbers so that x equals 5 and y equals 1, it is false. The ordered pair 1, 5 makes the sentence true and is called a solution of the sentence. The set of all such ordered pairs is called the solution set of the sentence. We can use the same set builder notation that we used for sentences in 1 variable. The set of all replacements for x and y such that y equals x plus 4. This denotes the solution set. What precisely is this solution set? Well, as we have already learned, this depends on the universal or replacement set, the particular numbers we are permitted to use. If U is this set, then the solution set consists of these 5 ordered pairs. If U were different, the solution set would be different. As another example, let U again be just the three numbers 1, 2, and 3. Let us now undertake to find the set of ordered pairs such that y is greater than x minus 1. U cross U, the set of all the ordered pairs from which we may choose, is easily computed. In fact, we've seen it before. All three of the ordered pairs with first element 1 will satisfy the given sentence, y is greater than x minus 1. If x is equal to 2, there are two values for y. If x is equal to 3, there is only one value for y. This set of ordered pairs, 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3, is the solution set. And its graph looks like this. Let us try the process again with the same universal set, but with a different set selector, namely, y equals x minus 1. None of the ordered pairs with first number 1 satisfies this condition. For if x is equal to 1, the sentence y equals x minus 1 requires that y be equal to 0, and 0 is not a member of our replacement set. If x equals 2, there is one value for y, namely 1, because y must equal 2 minus 1. If x equals 3, again, there is only one value for y, which is 2, because y must equal 3 minus 1. A graph of this set of ordered pairs looks like this. Now, comparing the graph for y is greater than x minus 1 with the graph for y equals x minus 1, we notice a very important distinction. In the graph on the left, when x has the value 1, there can be 3 possible values for y. Similarly, when x has the value 2, y can have 2 values. But look at the graph on the right. Here, for any value of x, there is only one value for y. A set of ordered pairs, such as is illustrated in the graph on the right, is called a function. There must be at most one y for each value of x. In other words, a function is a set of ordered pairs enjoying this property. No particular first element can appear again with a different second element. Thus, if we have the pair 2, 3, we cannot also have 2, 4, but we can have 1, 3, and 2, 3, for instance. As a final example, we will take as our universal set a number system used in high school algebra, the set of all real numbers. Here is the set we want to graph. The set of ordered pairs xy such that y equals x squared. The resulting graph is a parabola extending indefinitely into the first and second quadrants. This parabola is made up, of course, of an infinite number of points which have coordinates that satisfy our condition. Although infinite in number, they constitute a set of ordered pairs and are a subset of U cross U. Some teachers may wonder why we have restricted the term function to what used to be called a single-valued function. This restriction is made to eliminate the ambiguity otherwise inherent in such expressions as x squared plus y squared equals 25. If now we restate our description of a function in terms of a graph, we may say that no vertical line meets the graph of a function at more than one point. Let's try it. Here is a graph of a set of ordered pairs. Here is a vertical line. Let's pass it across the graph from left to right. Clearly, this graph does not represent a function. The vertical line intersects the graph at 2 points, giving us two values of y for a single value of x. The set of ordered pairs represented by this graph is a function. The vertical line never intersects the graph at 2 points simultaneously. Here is another. It is not a function. Neither is this. But with this parabola, it's a different story. This graph does represent a function. For a last one, let's look at this. Another set that certainly is not a function. In high school mathematics, functions have usually been defined by explicit, ready-made formulas. Thus, the set of ordered pairs that make up a linear function is defined by this equation, where m is not equal to 0. Similarly, the quadratic function is defined by an equation of this form, where a is not equal to 0. As we all know, such a formula defines a function. But the formula is not the function. The function is the set of ordered pairs to which the formula gives rise. Many students have merely been learning the formula without having either a clear or correct idea of what a function actually is. In the same way, a function defined by a graph should be looked upon as the set of ordered pairs corresponding to the points on the graph. The notation f at x signifies the value of y for a particular value of x. In the traditional treatment of functions, the symbol f of x has been ambiguous. Sometimes it stood for the function, sometimes for a particular value. One of the advantages of the approach we have presented is that this ambiguity is eliminated. F is the function. F at x is the value. The notion of function involves a domain, a range, and a rule or formula. The language of sets helps to clarify the meanings of those three words. The domain is the set of all first coordinates of the ordered pairs that make up the function. The range is the set of all second coordinates of ordered pairs that make up the function. And the rule assigns a unique second coordinate in the range to a given first coordinate in the domain. The language of sets helps to clarify the meanings of these three words. Domain and range are clarified because they are sets and should be thought of as sets. Because the rule is not a set and the function is a set, we can no longer confuse the two. The concept of set helps us see that the rule is not the function, but gives rise to the set of ordered pairs, which is the function. Thus, we see again how the concept of set can bring new meaning to the presentation of basic mathematical ideas in the high school classroom.